entries for the training entries and 10,000 for the test entries. So later on, we just basically flattens the data into 1D. Obviously, there are like more advanced techniques like Fourier transform, but we just stick to the most basic 1D representation in our case, because we just should focus on something else in these projects. So we also normalize the data. It's pretty evident based on the slides. You can go ahead. I guess there's
Okay.
nothing more to say here. So next thing that we have to do is we have to perform the feature selection. So here we go with like two things. So we use PCA to reduce feature dimensions. Why we do that? Because basically PCA is just inside the whole algorithm, we basically perform some matrix decompositions, and that's relatively irrelevant for our today's presentation as well.
Yeah, so
But
we
the
will do
idea is that
PCA. We will do PCA either next week. So
yeah, probably yeah, but we just
yeah,
do
of
this
course, you
with the
guys go
library
ahead.
function.
You don't need me. Yeah, you
Yeah.
don't need me. Go ahead.
So yeah, if I were to speed up, so we did this in order to like decrease the number of relevant features and to lower the dimension to perform for our model to perform better. So then we also apply lasso regression for the feature selection, but we go more broadly and explain broadly this topic later on. It's
Okay.
also in the slides. We're yeah, thank you. So no, you can skip it. So now our objective is basically to select and our basically best it's got to be 28 but multiplied by 28 features, right, if I'm not mistaken. So we do this by basically implementing this formula is on the screen. It's like a minimalization problem solution, so you can go ahead. It's also pretty evident. Yeah, so ridge regression is basically the a formula that we showed you in the most basic sort of form of the ridge regression is basically the formula that we showed you before. So we also basically train our model, and then we just extract the coefficients and store them into beta ridge arrays. So we then later on we just print it, and we can go ahead and next slide, please. And we just here's the matrix
Can you go
that
back one
evaluates our
slide?
performance.
Can you go back
Yeah.
one slide? So here, tell me about the how you set up the problem, because I see here that the coefficient is 10 times 142. Okay, so which means that the output of the ridge regression are 10 numbers, right? So I guess you train the binarized label, right? And you train the linear regression to give you the largest coefficients, let's say, to give you the coefficient closer to 1 for the correct label. Is that correct?
Yeah, exactly, because that's basically there are like tons of different features, and we just need to select the ones that
my
are
point
like,
is this. My point is this.
yeah.
You could have one scalar output, which is the output, and you make this output as closer to the label as possible. So the label should be 1, 2, 3, 4, 5, 6, 7, 8, 9. Or you can represent the labels as 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, right? And then you can try to have a model that outputs a 1 for the feature, for the position of the 1, and a 0 in all other coefficients. So you guys chose the second to train this second model instead of the first one, and I want to make sure that is that correct?
Okay. So, practically speaking, can you suggest whether that's the case?
I mean,
I'm
there
not
is
sure
no
what's
right or
the
no.
alpha.
There is no right or wrong. Right? They are both valid. They are both valid.
There is here
No,
like in the binarization of data.
No, but go to the
Normalize
Y.
the pixels
No. Show me the Y.
no, that's the other thing.
Either
I
way.
mean, yeah, Professor, I got your point. The idea is that I'm not sure whether you refer to alpha parameter.
Yeah, so I'm just checking that you guys did this. The output of the model are 10 different coefficients. Okay, you have 10 numbers in output of your model. You want 9 of these numbers to be close to 0 and 1 of these numbers to be close to 1. Correct?
Definitely.
And you understand that alternatively, right? You could have converted the output label into a number between 0 and 9, and you could have had a model that predicts one scalar, right? And you could have made this scalar closer to the label using it.
Oh yeah, definitely. Yeah. I got it now. So can we go to the next slide? In this case. So yeah, basically this our evaluation of the performance.
Let me stop this in
So
a second. Let me stop this in a second, right? So everything, so the worst number is 5, and 5 is most often confused with 3, which makes a lot of sense. And then
indeed similar.
8 gets confused with 3. God damn it, 3 is the worst number of all, right? Yeah. Yeah.
So yeah,
That's
that's results. And I
yeah.
guess we can go ahead here on this part 3.
Yeah. Okay, for part 3, uh, we apply Sobot filters and calculate the gradient, as it was indicated in the PDF that the TAs just gave us in the group for the challenge. Uh, as you can see here, we once we uh, vectorize the image into uh, in the solver for x and solver for for y, uh, we combine in both directions and then return the combination of that. Like, and the results for making the solver filter is to enhance the borders of the numbers, as you can see here in the original, and after passing the solver filter.
Very good.
Also, for the linear regression with interaction terms, uh, we generate the interaction terms here as it was also it exactly how it was shown in the PDF. And this is, I think, the most complex part, because we need to add bias term to we add a column of ones here in the X trains for the lasso bias, and also when we generate the interaction terms, and then also for the matrix of the sparse matrix conversion, which is the result of the interaction terms for the training and the testing data. One thing that I get confused
Yeah.
at the beginning was, what is the lasso? So this is a mathematical concept that implies the uh, like a penalty term to the model to prevent the overfitting. You can see here is the formula for this. The penalty is the sum of the absolute values of the coefficient scaled by a parameter alpha here, as you can see, which control the strength of the regularization. So you can see here, and why is this lasso is implemented. The feature selection, because the lasso tends to reduce the coefficient of less importance to exactly 0, selecting the subset of features. So when we are working with high dimensional data, which is this is the case, we can use some methods to filter the most important parameters of this dataset. Where we can use the PCA, we can use this lasso regularization. In this case, for the regularization, by adding the L1 penalty, the lasso reduces the overfitting and makes the model more generalizable to unseen data. This implies that if we are providing to the model a new input, like a new number that is not in the dataset that it was trained with, it can provide a more accurate result applying the lasso. Here is the confusing matrix
Much nicer.
that we get
That's much
after applying this. We get better results, as you can see, even for the number 5 that initially was one of the worst cases for our model.
Good. Now your biggest confusion now between the 7 and the 2, and that's also good.
Yeah.
So you see that
Because
before it was 3 and 5, and now you have 7 and 2. Very good. Nice.
Yeah, we can also get a classification report where we can show the precision for every number here.
Very good. F1 score, recall. Very good.
On the part 4, who's going to present this part?
I'll now go through part 4, which is the comparison between k nearest neighbors and linear regression. Next. So let us first discuss KNN. So in classification tasks, KNN predicts the label of a test instance by finding the k closest data points in the training set, and typically using distance matrix like the Euclidean distance. And it can also be used for both classification and regression tasks, although it's more commonly used for classification. And furthermore, KNN does not assume any underlying distribution of the data, making it flexible for different types of problems. Next. Moving on to linear regression. Linear regression is a parametric algorithm, meaning it tries to learn the best fitting line to map inputs to outputs using a mathematical equation. So it is primarily used for regression tasks to predict a continuous value. And linear regression assumes a linear relationship between the input features and the target variable. So in short, linear regression is designed for regression and not really for classification. So for multi-class classification, like this current data set, it has to be adapted, but this typically leads to suboptimal performance. So next. Moving forward, we implemented the KNN model, and the model is trained on the training dataset, and predictions are made on the test dataset. And the accuracy for the KNN was 96.88%. So the KNN performed slightly better than the linear regression, since it is a classification algorithm. And linear regression predicts continuous values and then adapts them to class labels by rounding. So it is not inherently designed for classification, which might explain why it is performing slightly worse than the KNN. So with that, I will now be passing the time over to Tsai.
Okay, next slide. So now I'll be going through the gradient descent for linear regression. So we use a batch gradient descent. So what this does is that it uses the entire data set, and it computes the gradient using all the data points at once. And it updates once per iteration. So after computing the gradient from all the data points, the model's parameters, which is the beta, is updated once per iteration. So the gradient is the average of all the errors, the difference between the predicted and actual values over the data set. So you can see on the right, we have like the loss history graph for the mean square error over all the iterations. So we can see that our models for the batch gradient descent, the closed form, perform very similarly at the end of the iterations. Next slide. So this is the convergence of parameters for our gradient descent. There's a lot of parameters, so it's quite hard to see. But basically, like as the iterations increase, the parameter values they start to stabilize, indicating that the gradient descent is finding a solution, and that the update to each parameter is becoming smaller and more consistent. So they're approaching their optimal value and basically converging. Yeah.
Have you seen? I'm thinking about what's the movie with the time travel that I'm thinking about? The Christopher Nolan movie with the time travel. Guys, help me. Guys, help me. What's it? No. With the
Interstellar.
Tesseract. Yeah, that seems like a scene from Interstellar. This this plot here. You have all the different futures and all the different paths converging together. Go ahead. It was a joke. Nobody likes my joke. Anyway, it doesn't matter. It looks like a scene from Interstellar. Go ahead.
But yeah, so we can see that some of the parameters, they converge to positive values and others to negative, which indicate like their varying feature importance in the model.
Correct.
So yeah, that's
So is this
and
this is without lasso, right? This is without lasso. This is just a plain L2 node, right?
yeah.
Yeah, because you
so
could
that's
try to
the
implement lasso, and then you would anyway. You will go ahead. Yeah.
yeah, no, that's it for our presentation. Yeah.
No, that's it. Okay. No, it was a good job. Good job, guys. Very good job. Yeah. Okay.
Yeah, that is the last slide in our presentation. So if you want to see a little moment of Oracle Lab, here
I
is
just want to see how you convert the 10 continuous values into a label. Do you take the max? Do you take the? Show me that conversion there, because when you calculate the error over the MSE of the label, I just want to see that one there.
precision. I think this is not the
That's
latest version.
KNN.
Yeah,
Let me just see how you convert from the 10 coefficients into the binary label. I just want to see that operation.
Okay. It was divided by.
When you do the prediction, right? Where is the PCA? Very good. PCA is very nice. Yeah. Y1 hot. Okay. Regularization term. Evaluating the performance. Reach argmax. You see that you do an argmax. There. Stay there. Go up a second. Go up. There. Look at this. You see that you do argmax, right? You do argmax. Do you always do argmax?
I didn't write this part of the code. It was Inmin who.
Yeah. Is that
did
what?
this part.
Yeah. Can you just confirm that this is how you always convert from the continuous label to the binary label?
Yeah.
Yeah, I think that's what we are doing. Yeah.
Good. Okay, interesting. I just want to compare with the other group. And you guys, let me just see the accuracy. Or take note is 96 point something, right? 96 point something.
Yeah, it was around 96%.
So 96 with just plain linear regression, and then you have the swabble. Then okay, and KNN was 96.5.
The test accuracy was 97.
Good. Okay, very nice. Guys.
For most of them, the values were between 96 and 99%. I think the most efficient one was for 0 and for 1. Yeah, 98 and 99 respectively. The KNN model, the test accuracy was 97%, and with the linear regression was 97. This was just a little different, a small percentage here, but 97% in general.
Nice.
Okay.
Very good, guys. Elton, do you have any question for them? Do you have anything to share?
Like how long do you the complexity comparison with the linear regression and the KNN? Do you have like how long does it take to train the KNN and linear regression? Do you have any?
Sorry, but we didn't exactly have the time taken, but
Like roughly.
All right, but
quite,
you run.
quite
Yeah, run.
fast. Yeah.
Okay.
Yeah. Thank you.
Okay. Oh, Elton, go ahead.
So next thing I think is Castle Grotto. I don't know how to pronounce it.
No, you have to. What do you mean? Is disrespectful to the people from South and Central America, from Latin America? Of course, you have to know how to pronounce it.
Castle Grotto.
Guys, can you please teach?
Okay. Quetzalcoatl.
Repeat, Elton. Repeat, Elton. Repeat.
Castle what?
You have to be multicultural, Elton. You know, you have to embrace all languages and all cultures. You know. Go ahead, guys. Go ahead, please.
So our team members will prepare the slide.
Joyce, how do you pronounce the name of your group, Joyce?
Quetzalcoatl.
Very good, very good. You have to imagine life. Guys, my life is very boring, right? So this is how I have a little bit of fun. Go ahead, please.
Okay. Give me a second. Share screen. Oh. Nope. Nope. There we go. Okay, can you see my screen? Or the slides?
Yeah.
Yeah.
Okay. So this is our presentation for challenge 2. In it, we had to analyze the MINST data set. In the MINST data set, there are just handwritten numbers. Each number is contained in a 28 by 28 image with pixels ranging from 0 to 255. So there's a gradient, and in it there's 60,000 training pictures and 10,000 test pictures. And since there are so many pixels, in order to reduce the amount of data that we're analyzing, we decided to do some feature extraction. So we looked at every pixel and saw which pixels are most important to classification of the images.
Luigi, tell me, where did you get this idea of the mutual information between the pixel and the label? Where does it come from? Where does it come from?
For that, you have to ask Joyce, because she did this.
Joyce, tell us. Where did you get this idea of the mutual information, please?
I think this is stated in the description in the challenge. It asks us to do the feature selection for different pixels. So that is why I use this.
But where did you get this concept of mutual information? Where does it come from? I mean, did you have it before in the class? Did you look it up somewhere? Was it suggested by ChatGPT? That's my question. I just want to know. I'm just curious about it.
I think I check it out online and also for ChatGPT.
Yeah, because it's a very powerful tool to estimate dependency between two random variables beyond the linear case. Okay, beyond the linear case. But the issue is that this measure is very hard to calculate, so it's very numerically unstable. So that's why I'm very confused by this plot, because you have like if you could give me this, okay, do this for me, guys. You give me this as an intensity plot, okay? So you go back to the 28 by 28, and you give me an intensity plot for the value of the mutual information, okay, guys? Because here I don't know what I'm seeing. I think that what we are seeing is that the edge of the 28 by 28, you have a low mutual information, and since you vectorize the quantity, then the edges appear every 28 bins. So you understand what I'm trying to say, guys?
So basically, yeah. So we first put because it's a 2D vector. We first paint it into a 1D vector, and then yes, every 28 it would go back to the left side and the right side.
Yeah.
So you have these like troughs.
Correct.
I can't really. Correct. You have these troughs where yes, it would be on the sides where there's normally nothing there, so it doesn't matter.
That's my.
And then in the middle here would be the middle pixel is normally is changing somehow, or there's a lot of change in that pixel. So I'm assuming that there's a lot of information in that pixel that can be, extracted. Whether it's on or off really helps to classify whether a number is like a 4, for example, which normally doesn't have anything in the middle, or like a 8.
That's awesome. Yeah.
Does that make sense?
Very good. Yes. Okay, go ahead.
And then we used, and then we calculated beta by using the formula that was given to, given to us with this regression term. I forgot what it's called. With lambda, which prevents overfitting. What was it called?
Ridge regression.
Yeah. And doing that, we then calculate the prediction by multiplying the test data set with our beta, and we got a very low accuracy of 23%. But as you can see, it's like sticking on the line. But I feel like the main problem isn't the actual like classification. It's how we put the number, how we change it from a continuous system to this numbers from 0 to 9, because you can see it's misinterpreting 1 as 0, for example, which doesn't really make any sense. And like 2 and 1, like it's always close, but it's never on it. We did that by clipping, which
okay, go ahead.
So yeah, I don't know if I can show you it because it's not. I should just share my whole screen. Oh well, we did it by clipping, which I think is not a very well, as you can see, it's not very good. But then oh yeah, and then we so this was without our feature selection. We got an accuracy of 23.02, and then we implemented our feature selection, which was based on this the mutual information, and we in fact got a worse accuracy. We got an accuracy drop of 3% when we increased the threshold. So when we increased which pixels we take into account and which pixels we don't take into account. So to be honest, I'm not sure why that would happen.
Well, I mean, you're using less information, right? So
yeah.
But the issue here is not. Yeah. Let's see where this goes. But
no, I think that's it for section 2. Yeah, and then we have section 3.
Okay.
If someone from our group wants to present section 3 and section 4.
Hello. Can you hear me?
Yeah.
Okay. So for part 3, we focused on extracting feature representations from grayscale images representations of numbers by dividing them into smaller 4x4 patches and computing 3 key patch-based features. Those 3 main features are mean intensity, gradient magnitude, and dominant gradient orientation. So for the intensity, we capture pixel level information. And for the edge strength and direction, we try to identify structural patterns. The gradients are also computed using the Sobel operator called Sobel, which calculates the changes in pixel intensity along the X and Y directions to measure edge strength. Basically, when one value has a very sudden shift to detect an edge. However, rather than just computing the gradient orientation for each pixel, we also applied dominant gradient orientation. This finds the most frequent edge directions within each batch and plots this data into a histogram of gradient orientations. And it selects the orientation with the highest occurrence. This offers a better representation for the patch's overall directionality. And here you can see in the images, the original image, then the mean intensity for the 4x4 patches, then the mean gradient magnitude, like the edge strength, how strong of an edge is it. You can see that, for example, for the little head of the number 5 there's a really bright white followed right by a really dark black, like on the top of the 5. So you can see in the mean gradient magnitude, 1 pixel on the gradient is completely white, and then the ones next to it are black. That's just to give you an idea how to read that graph. We also have the dominant gradient orientation. I don't really know how to read that graph. I cannot really explain it. I imagine that it's when there's a really sudden shift.
Yeah, but you can see,
Gradient.
you can imagine it, right? So the color changes from black to white, right? And so you see the which direction the change is, right? Because you have 4x4 patches, so you have 4 possible directions. So this makes sense.
Okay, so also part 3.2 is in the slides, but I'll just explain it shortly. It focuses on we then focus on enhancing feature selection by combining mutual information and interaction terms. First, features with the highest mutual information scores are chosen to reduce complexity and focus only on those relevant to the target. And after that, those features are expanded using polynomial interaction terms to capture relationships between pairs and features. Regression. Okay, I'll just leave the.
What accuracy do you have when you add this the interaction terms and these transformed values? Here.
What package?
No. What accuracy? So you still have.
That's the accuracy. It's
Oh,
still really low because it's still using
we'll discuss it later.
regression.
We'll discuss it later why screwing up.
Yeah. Okay. So we can see the accuracy is still really low, even though we have a really detailed set of features. And I'll talk about that in the next slide. So can you go to part 4? Okay. So basically, the reason why we have a low accuracy, even though we have a really detailed set of features, is because we're using linear regression. And since the task here is to identify numbers in images, that would be a task better suited for classification, because even though we have a lot of features, a lot of data to work with, the data is not really linearly separable. So we can see in the, can you go back to the confusion matrix, please? We can see that it does make accurate predictions to a point, but it has to compromise because it has to separate the data with basically we have a n-dimensional data set or data set representation. We have to separate with a n-1. So we have to do some compromise. We have to separate the data into 2 fields, and sometimes that's just not possible with a low error. We cannot minimize the sum of squared errors. So here we can see that the way we did the model, it particularly struggles with the number 4. It often misidentifies the number 4 and also the number 9. And the notebook, we had a little box plot. You can see that 9 gets mistaken for 8 a lot. Okay, so can you go back to part 4, please? Thank you. Okay, but you can see that, for example, if we apply KNN, K nearest neighbors, or logistic regression instead of a linear regression, we actually get a much better accuracy. That's just because it's those prediction models are better suited for tasks like this, since they can make use of the features more effectively. You can see a comparison between the k-nearest neighbors and the linear regression and the following slide.
Also, that logistic regression, we're going to see it at some point. So, yeah, absolutely. We have to cover logistic regression. Yeah.
Yeah, KNN is only slightly better than logistic regression because the features are really detailed. So the classification can be done to a great effect. Okay, so anyone for part 5?
Yeah, I'll finish it off. So in part 5, instead of calculating beta outright by taking a bunch of features and then doing that big calculation, which is very inefficient, we can instead do in my opinion, seems more inefficient, but probably slightly more efficient if you have a larger data set where we do a gradient descent, where we're looking through each beta and changing it by a very specific amount each time to get until convergence. So first we have to start with an initial beta. In our case, I chose a beta of 0. It could also just be a random number, but I felt like 0 is fine. And then I calculated the mean squared error loss using this formula up here. And then we had to calculate the gradient of the mean squared error loss, and then we can change beta by subtracting the mean squared error loss from beta and multiplying it by this learning rate. And we do that until the mean squared error loss doesn't change very much anymore. And that's when convergence is reached. And we can use our beta to actually predict numbers. As you can see, it's still not very good. With a convergence of 1e minus 3, we got an accuracy of 21.71. This is still just using the whole data set. I did not
Patch it.
I wanted to compare I wanted to compare between the normal one and the gradient descent, so I didn't add any other special like FFT or anything. I just wanted to compare the accuracy between them, and yeah, it's still pretty bad. And that's it, I think. Yeah.
Yeah. So guys, so there were three of you, right? Working. There were 3 of you. Correct. How many people were in the group potentially? How many people?
We have 5 members.
But how many were active?
All of us are active, but
Okay.
some of them are in charge of coding and not for
I see.
presentation.
So they didn't present. Yeah. So but for me, guys, can you pull out the collab? For me, guys, the problem with your presentation. Yeah, go ahead. Can you pull out?
I was
Okay. Okay. Can you pull out the collab quickly? Because for me, guys, the issue that you guys had was an issue of of creativity, right? Because of course we are telling you to use a linear regression model to do classification. So of course it's not going to work. And you didn't, in my mind, you didn't explore the space of solution enough, right? Because you stick to the model where you do the linear regression, and you didn't think how to modify the settings so that you can have a better performance, right? So you see what the group before did. The group before, they didn't predict the number 1, 2, 3, 4, 5, 6, 7, 8, but they predicted the vector of 10 numbers, and they just picked the largest number of this set, okay, as being the label. And by doing that, they achieve a better accuracy. For example, here, right? So you see that your Y label, go to the Y label. You see the white label here is given to you as 1, 2, 3, 4, okay? But it's clear that you can reorder the numbers. And if you reorder the numbers, nothing changes, right? but you will get a better accuracy. For example, the number 0 is okay, number 3 is okay. Then it's clear that the next group should be 3 and 5, because 3 and 5 look very similar, right? So if you flip 3 and 5, your model will do better, right? Because you are trying to, yeah, you see it here, for example, right? 3 and 5, right? You see that on the representation perspective. Okay, I'll try to give you a high level description of this, right? So the model is moving, right? And it's making prediction. And you, since this is a regression model, you would like images that are close to have labels that are close. Okay. So of course, the 1 and the 2, they are not, they are sort of similar, but not terribly similar, right? But it's clear that, for example, the 3 and the 5 are very close. So you should sort of help your linear regression model by putting close labels to images that are close, so that the model is sort of linear interpolating over the space of these images, right? For example, what else is close, right? The 7 and the 1. No. Yeah, but you understand what I'm trying to say. So if you just reorder your labels, you will get an improvement from the reordering of the label. Another thing that you could have tried is to use multiple models and just classify numbers, classify one numbers versus the other. Right? You could have had just one classifier to say, is this number 0 or something different from 0? So you will have had 10 models, and each of them gives you a prediction. Then you pull the predictions together. Or you could have had another model in which, I don't know, what else could you do? You could have a hierarchical model in which you first classify, let's say, 1, 5, and 3. You classify one group of numbers versus another group of numbers, and then you refine it to a 3. So basically, I think you got stuck into focusing on the original model, right? And you didn't think that you had the freedom to change the problem settings so you can get a better prediction, right? So just remember that for next challenge, you can do whatever you want, right? Of course, we try to make it challenging for you guys. So we cook up a problem that makes no sense. We cook up a problem which is artificial, but just for you guys to explore the space of solution. Do you understand what I mean?
Yeah.
So yeah.
I also wanted to, like, yes, there are some like mistakes with 3 and 5, for example, right here, this one from 88, but it's mostly, in my opinion, the main problem is the things around it.
So, but because this is what I'm saying.
Like when it's specifying 2, it thinks it's a 1.
Okay.
Why?
We can spend some time on this. Okay, so can you imagine that these images, they live, let's say, in a space? Okay, so imagine that you have the space of all images by 28 by 28. So imagine some high-dimensional space, and then you place the points that are in the data set along this space. My question to you is, what do you think this space? What do you think the distance between images in this space look like? Of course, some numbers are closer to some other numbers in this space. Then you imagine what the linear regression is doing, right? The linear regression is trying to pass some sort of linear relationship between this space, okay? So the linear regression is reconstructing a distance between images with its prediction as the projection over this plane of dimension 1. So what you're observing here is that when you have this high dimensional space of all images, and you project down to one dimension, right? The closeness of the images is lost, and you are artificially producing close predictions of images that are very different. So, for example, why here you have that 1 is confused a lot by 3, or like it doesn't make sense, right? Because the 1 and the 3 are very different. But when you do this projection does, you know what I'm trying to say? This projection crosses over images that are far away and makes them appear very close. So this is artificial from the fact that the projection that you have breaks the geometry of the high-dimensional space. So the high-dimensional space is a geometry which is very complex, that where the similarity between the 7 and the 1 it's there, right? You just change a few pixels, you go from a 7 to a 1. But the way you do the projection doesn't preserve the distance in this high dimensional space, and so you lose. You see something artificial. Like you have a low dimensional representation which is not faithful to the high dimensional space. Do you understand what I mean? So
Yes.
Okay. There is this idea, right, that there are some projection to a low dimensional space that are useful because they preserve the distance of the high dimensional object into lower dimension. And there are some projections that are useless because they do not preserve the geometry of the projection. And my point is that what you guys cooked up here was a projection. It was not good because it did not preserve the geometry of the high dimensional space.
Yeah.
Okay. It's not a critique. You guys are going to do better next time. I just want to explain the logic, because I know that you guys did the press like, oh, why did they give us such a stupid problem? Why are we doing a classification with a regression model? It's because we wanted you guys to think about it. Go ahead.
I'm done. I don't.
I just don't want you guys to be angry with us. That would be something like that. Okay. Anton, any comments here?
I think everybody would like to have a presidential class with Alton. We will give him a very warm welcome.
Come again. What did you say?
I don't know what everybody thinks about that.
No, come on. What did you say, Francisco?
No, it was a joke.
Okay, oh, you hate Elton. I understand. I remember, if there is a mistake, it's always the TA. It's never the professor. The professor never make errors.
I just link to a video of 3 Blue 1 Brown in YouTube, which explain it's not exactly the dataset classification or the linear regression model, but explain some concepts that you might find useful to this challenge. So if you want to look, I give you the link there in the Meet chat.
I think more that if you don't know this YouTube channel, you should thank you should thank Aldo for the suggestion, because this YouTube channel is amazing, right? This YouTube channel, it's very good. I hate a couple of YouTube channels because these people are smarter than me, more good looking, and have more money than me. And one is the Veritasium channel. The other one is 3 Blue 1 Brown. Yeah, there are a few channels on YouTube that are problematic for me. Yeah. So should we do one more group and then take a break, or should we take a break now? Break now or after the next group? 0/1. So Elton, you can call up the next group if you want in the meanwhile while we see for simulation. Okay, everybody. Joyce wants now. Let's see if anybody else answer. Oh, we are even. No, now we wait. Now we wait. Okay, good. Elton, call up the next group, then we move on.
Next one, green thing.
I haven't been able to make a presentation, and I also just now while trying to fix a thing with the code, it broke, so I'm trying to fix that. If I could do it after the break, that would be lovely.
Okay, no problem. Also, if you want to do it next time, there is no problem, right? I mean, it's no problem for us. Okay, Elton, call the next one, please.
So next, this one is Alicando.
Hello, Alicando here. Can you hear me?
Yeah. All there.
Okay, is Fran around here? Oh yeah, he's right there. Maybe he's taking part of the presentation. So please, Fran, go ahead.
Okay, so let me present my slides. Hope you like my title. How do you? Oh, okay. Well,
your presentation slide is very nice presentation. Yeah. It brings me back 20 years. Yeah, go ahead.
Yeah, really nostalgic. So okay, I will going to try to do it as fast as possible. So I think everybody wants to press already. So I will not talk much about the. This will be a presentation more of or more than anything of struggles. So what kind of problems we face upon this challenge? So let's see. Okay, you guys already know all of that. You already experienced that. So we get the data set, blah, 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 right? And then we talked about this last time. We didn't have pretty good accuracy because of the high dimensionality of our data. So that's why we tried to improve this time. I already showed you this last time. So, okay, so the first thing is like modifying this beta 0, which was like the intercept line, and we didn't get the results. Okay, next thing. You can look at the table here. It was not very useful. And then, okay, so, okay, here, the interaction term. So what we did next was doing this, like extracting the different features that we had in the document, like the gradient and all of that. And then we had another challenge there, which was how to select the most important ones. So to give it a first try, we just select all of the combinations. I had to say that too. So it was a little bit, not a little bit, it was way more slow, but we got better accuracy. So we think that this is actually a very important problem, but we didn't have enough time to get to it and to select which one are the most important features. So what we did was using all of the combinations, which is a very expensive computation. But here's like, here we have a better result, like we have 43% of accuracy with this approach. And we can see that we have like the same problem as before. Sorry, the same problem as before, like our labels are not in the place where we want it to be. And we will talk about this now. Like this was the last time that we attempted to do this thing, like getting one continuous variable and then try to round it to one number. That is, I think, the biggest problem with this challenge, right? Because we will talk about now. Number one which was the sorry, I think I have it here. Yeah. Oh, like the prediction method. So we have a matrix of pixels, and then we have to put that into one model, into one linear model, find the best coefficients, and then we have to output one single number and round it. Like that is what is stated in the original challenge. And then are we assuming like that we have some kind of parameter in which like 0 is like we have this kind of order in the numbers, so we can exactly know where we have like the 1 and the 2 and the 3. And that is why we can see like our confusion matrix looks like this. We are not able to actually very well, like we are kind of there, but it's not a very good model, right? I think, is everybody following?
Yeah, this is what we discussed in the previous presentation, yeah. Right? Identify the idea that. So
this is one thing we have to solve to fix, and then the high dimensionality. Like we have too many pixels, and some like using so many numbers and so many variables it's not very useful and actually makes the computation a lot heavier. So how to get better features? We tried to get Fourier analysis, but we couldn't get any useful information from it. What we first tried was to use the Fourier coefficients, but that was not enough. We used a lot of Fourier coefficients, and it was not enough, and we couldn't find another way to get useful information for that. And then I thought that before moving to anything else, because we were suggested to use convolutions, but then we have another problem after looking into convolutions. Here I have like a little reference for you to try to get your head around it. So basically we have to pre-process this image so we can get a better, in the end we will have to reduce have less inputs and more significant ones. So you can imagine it like as a first idea of the convolution. If we had like a machine in which we can put our image, and then we can have as an output a better set of parameters, which is very significant, which tells you a lot about the original input, but which is more manageable. Okay, so.
But this is a convolutional neural network, basically. What you're describing is a convolutional neural network.
Yeah. Oh, okay. So here I try to explore to use this idea, and here you have some examples of some convolutions. I didn't get any good results with these ones, obviously, but I just wanted to show you so you can get to the idea. And then, okay. So basically, the hard thing about making agreed convolutions in our case is, like, we can see the right image. So we have one matrix that is traveling across the values of our images, and we set this matrix to some parameters that can output another matrix which we expect to be more significant. So we can take the same information out of this matrix and it is compressed, so it is actually easier to process, right? But the problem is we have to actually set these parameters. We have to know which kind of values we put in all of these matrices, so we can have some significant information after that. And because of the challenge this implies, we just skip this approach. I don't know if because this is suggested in the challenge, I want to know if, and I didn't see anybody use this for the challenge too. I want to know if Alson or anyone has anything to say about what kind of approach could we take if we were supposed to use the convolutions.
I mean, I because for me it's hard to put myself in your shoes, meaning that like my first approach would be to take a pre-trained convolutional neural network, and I will just steal the convolutional core from the convolutional network. So the convolutional neural network will learn useful features extraction. So I will train a very simple convolutional neural network on MNIST, and then I will just steal the convolutional cores that the convolutional neural network does.
Yeah, because
of course this is a topic, but this is a topic that you guys don't know, right? Most of you guys will not know about CNN. So yeah, go ahead. What was your comment?
Okay. And then, okay, let me see. Yeah, I actually was very enthusiastic about this idea, and before giving it up, I look at some methods of some paper that some guy I don't know where published, and it was using linear regression but performing this kind of convolutions before. And what they did is actually create like a random sample of values for these matrices, and then an enormous range of values for these matrices, and it was just the effectiveness came just by randomness, and then they will like filter this out and just maintain the better ones.
Yeah, of course you could do that because basically the linear regression will always give you, if you do linear regression, you will get a score of how useful the feature is, right? So if the feature is not useful, you just throw it away and you start to. I understand. I mean, it's very time consuming, of course. So you could get to something.
Yeah. Okay. Moving to the next thing. Okay. So I said, okay, we have to be able to use this thing to somehow get something useful. So what about selecting the features in another way? Like we want to select the ones with the most variance. Maybe we can get something out of that. So we select them according to variance, and then we have like the top 300 one, the top 100 features with more variance. And the interesting is that we have some similar result, like with the top 300 to our previous model. Like our previous model was not very good. It has like 26% of accuracy.
Yeah.
But I think it's interesting that we can obtain something similar by just using 300 out of the 700 original features we have. Anyway, we don't have any like amazing result out of this. And the less we use, the worse it gets. So just to explore it a little bit. And then the next thing is like this rich regression. So I will be honest, I just saw this method and I just applied and then tried to understand it as the best I could, because it's just very amazing that you just do a little modification to your model and you can get like way better accuracy, right?
So this was the most valuable lesson that you learned from this, right? You learned the power of exploring models, right? That was. Go ahead. Describe your feelings of this.
I don't know if I feel any, I like I'm sounding too passionate about this. Okay, so if anyone can get a better interpretation of this, I would like to hear you so we can get like a richer knowledge. But one simple way that I can put it is, we have lots of features in our model. Like I will try to explain why we can get a better accuracy for this. So, well, let's compare, like let's have like an ideal set of numbers. Let's imagine that our matrix is like with more pixels, and all of the numbers are the same. Like we have the numbers follow the same pattern. So if we train our model in this kind of data set, and then our numbers were exactly the same as this one, like we will have like the ideal model for every number, and our neural network will need to actually learn anything. It will just be like a perfect mapping, like we input it and we have the correct answer.
Correct.
But as we introduce like more variance in our data set, like here all of the trees are different, and we can know because we have like a model of a perfect tree in our head and we can know the difference. But when it comes to a machine, it's different. And what we try to do is try to model to learn all of these shapes. And how we do that is we have all of the trees and we input as a parameter. But because of the variance, like the variance is very high, sometimes they are not perfectly centered, or the height difference we have in the strokes, in the thickness of the line, and all of those separate like variables. Sometimes the model tries to like fit too closely to these parameters, and then it fails to predict the numbers that are outside of what the model learned. So we want to penalize that kind of overfitting, and that's why we use this lambda. So we can say to the model, okay, don't freak out if you see one kind of number that is like, don't stick too much to the actual information that you learn from here, and try to fit to the more general case of the things you want to predict. So we are like penalizing the model for fitting too strictly to train data set. Is this correct?
Nothing to add. Nothing to add.
Okay. So that's why we can obtain a better accuracy here. And that's the best improvement we have made in the model. And then...
Okay, let me ask you a question. Can you go back to the formula? One more. Here there is the lambda. How did you choose the lambda? The choice of the lambda is all, as we always say, right? The choice of hyperparameter is just as difficult as the choice of the model. How did you choose the lambda?
This was just the suggestion I get. I saw that this was typically used as this value. Yeah,
No, but I mean, so did you experiment with different values of lambda? What accuracy change they give you? Because you could do a nice, for the final presentation, please do a nice plot. Put the lambda between 1 and 100, whatever, and see the difference in accuracy as lambda changes, please. You'll see you see other amazing things that will enrich your future life for sure. Go ahead.
Okay. Okay, and then we implemented this very in the sense, but we did it with the other model, like when we didn't implement this regularization. But however, we can see here how the accuracy improved. The maximum was like 26 with the previous model that didn't have regularization. So now we have to implement it with the new one. But I just wanted to show you this graph, like how it is increasing as the iterations go up. And yes, that's what we have until now.
Okay. Elton, any comment for them? Any question for them?
Have you tried to, so you just implement all the algorithms by you. Have you tried to compare like something like library and compare your results with your algorithm?
I actually didn't show here that we implemented KNN.
Okay.
We used it with the library, with the Skype library, like the function was already built in. And it was quite amazing for me, but I didn't put here because what you do is you get the raw pixels as the input, and it can get you like a 96% of accuracy. And I don't know what happens there. For me, it's like a magical box. You just put the pixels in there and it gets you the accuracy. So I didn't want to emphasize that. And yeah,
I think you can just see the source code. If you are using, like, for example, if you're using VS Code, you can just F12 into the library, and you can see actually how they implement the algorithm. And I think you can learn a lot of things from that.
Okay.
That's a good suggestion. Good suggestion. Yeah, there are a couple of nice interviews. You can look them up or a podcast with the people that were working on the core Python libraries back in the days, right? Because Python is maybe 10 years old. And there are some people that participated to the core code of Python for this, like packages, let's say, and NumPy and stuff like that. And, you know, it's a very interesting thing, because of course the code is for everybody. So the code is free. So these people were working without being paid, and they did choices and they had a view on what they were doing, and it's very interesting. The same with Linux, right? When you go to a function in Linux, you can see who brought the function and when it was authorized, and you can see that the functions that are most at the core of Linux, they always have the Torvald permission, and it's very interesting to see how code has emerged for this application. Okay, very good. So guys, we're a little bit late. Let's come back to 8:45. Okay. Let's come back at 45. So I give you 9 minutes break, and then we go with the presentation. Okay, go walk around, get some water, pet your cat. We're talking 45. Mm.
No, male, dai, no. Tamu!
Tamu! Oh,
Tamu!
sta ridendo, Tamu.
Tamu!
Sono uguali. Ah, guarda il sole, Arti.
Quello è il sole, papà!
Sì, c'è il sole.
Girati! Girati, papà!
Gira.
No, sto facendo il video, Titi. Vieni, vieni.
Girati!
Titi, sto facendo il video.
Girati!
Dopo, dopo.
Girati! Girati!
Sto facendo il video, Titi.
Girati! 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 Girati!
Piano, piano che cazzo. Piano.
Usciala. Andiamo, Titi, corri.
Gira la borda.
Riesci a prenderlo, papà, Titi?
Aspetta, ma che così là? Ho tutta la strada che non giù da sola, ma che no?
Titi, vuoi il bastone?
No, voglio salire!
Che corsa, no? Là.
Sì, è bello! No! Stop!
Sì, bravo. Oppure hai cambiato le scarpe. Sì, che corsa. E adesso cade papà, digli va che c'è il buco papà. Buco.
Sta a monte.
Ah, non ci sta. Oh, mamma mia.
Ehi.
Guarda se prendo il sasso. Quello da parte, Atti.
Stato il sasso.
Quello lì è freddo, ne?
Oh, freddo il sasso.
Ghiaccio, ne?
Andiamo, Titi, vieni,
Vai.
andiamo.
Si lava le mani.
Vieni, vieni, Titi, dai.
Mi scappa.
Cavallo, cotta prima.
Dove la cazzo?
Di ciao, Titi, di ciao. Ciao. Dai, dai, vieni, vieni.
Cosa?
Vieni dai papà. Vieni, Titi.
Non cammina, corsa.
Cavallo.
Hello, guys. We're back. Griffin Group, do you want to go now? Do you want to go after the? Do you want to go through the midterm? Make your guys down.
I'd rather do now.
Okay. Good. Look at the stress in the voice of this young student. Go ahead.
Happens.
It happens.
So,
because they're a tough life. Go ahead.
I will just open the right one. Which one is it? No. That. So if we go all the way to the top, like everyone, I loaded a lot of libraries and fetched the data set. This command that I used was later discovered by a friend of mine and me that it did lead to a few outliers, which did some problems for the gradient descent method. But I'll get there when I get there. Then I set up some functions that I would use quite often. This one is an old one that I don't use anymore, but this was just to plot the image. This was to take away the gradient in the number, so they were either fully colored or not colored at all.
I see. So you binarized it. Good.
Yes, and then I also, because I later changed the value of the labels, so I didn't attach them to the number in the picture, but had it be completely free, I had a function that allowed me to do that. I started off by examining what I was working with and looking at a random instance of this picture, and just to know what I was dealing with. I also tried a normal linear regression just to see what the absolute baseline is, with the number of the image being the label. And as you can see, it is very bad at predicting with only 24%. And when you show the confusion matrix, you can see a line, but it's kind of shifted to the right in the beginning and to the left at the end, trying a bit to reach the middle, which is not surprising considering they will take the average of two different ones. And if they're on opposite spectrums, they will go towards the middle. Afterwards, I considered different ways I could change this image to make it easier for the computer to find patterns and identify different behaviors that would be useful for it. So I tried FFT, and I first created some functions that could be useful, just applying the FFT, a high pass filter, and an inverse FFT. I did notice, however, that I couldn't just use one function for each of these. I had to kind of copy and paste the previous function, because when I transported it out into a reshaped it back and then threw it into the next function, it did lead to some errors, which created nonsensical FFTs and nonsensical inverses. Therefore, I just, in the final inverse HP FFT, it practically does everything these two do.
Yeah, because I don't know what's your background, right? But basically, the FFT is designed for complex numbers. Where if you have only real entries, then the FFT has a certain symmetry, and so basically that's what you're seeing. That's what you're seeing. That the transform itself was originally designed for complex numbers. Go ahead.
Yes. And then I started off to see if the FFT itself could be useful. So I just created what I called flattened image where I made it binary, because that helped the FFT a lot to find clear features. And then I used the FFT just to see what we're dealing with. And the center has to do with all the low frequencies. So all the times where it's very straight and doesn't change any color. And as we go towards the edges, it deals with the different higher frequencies. So as you can see, we have a very much low frequency focused, which is very clear, because if you go from left to right here, you see that it goes black, 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 white, 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 black, black, black. And that can also be seen here, how on this axis, on the x-axis, it's also many in the middle and the end don't appear at all. And it's less of a low frequency in the y-axis, because here we have this and this line. I tried to see if doing just FFT would improve the linear regression, but it did not, and it actually made it harder to differentiate. Then I attempted a high pass filter to emphasize the edges. So I took the middle and just set that to 0, which also allowed us to clearly see the frequencies further away. And it gave us something scary like this. And then I did a linear regression on this, and it had a slight improvement, but barely noticeable. And we did the computing matrix. I noticed that it got better at identifying the more straight functions, but like 1 and 4. But it got worse at the more curved functions like 8. That one got a more spread.
Nice.
And it also identified it as 6 a lot more than it did previously.
You say 8 and 6, right? 8 and 6.
Yeah.
Yeah.
So 8 turned into 6 more often, although 6 did not turn into 8. So there was some preference towards the middle number, which I've already assumed previously. And then I tried to see if I could split it up into categories of numbers that look similar.
Very good.
But I very quickly realized that using normal, I would have to go several stages to make anything useful, because the accuracy was already 73%.
So if you had 3, so how did you form these 3 groups?
I did it by choosing numbers which had straight lines, being 1, 4, and 7, and very curved or circular. I gathered together, and the rest, the ones that were a bit in the middle, because 2 could very much be seen as 7 sometimes, or as 9, as I'll show you later, which made it a bit in the middle, and same with 5 and 6. I put here because it had a lot of similarity with 5. And I wanted to spread it out a bit more evenly. Otherwise, I would have put it in group 3 as well.
And by doing this, you obtain an accuracy of 73% only.
But only on identifying which group it is.
Yeah, of course.
Which was, and I also didn't put them in the order of 1, 2, 3. I noticed that I wanted to have the first group in the middle, apparently, and the third group, the first group and the second group I wanted at the edges, and the third group I wanted in the middle, because it was larger, so more numbers were attracted towards it. It did increase from, I think it was 60 something accuracy to 73. But once I saw that I couldn't really do, unless I went deep into trying to optimize this function, I would have already lost a huge amount of accuracy, and expecting a linear regression to do a good job at classification after already having lost more than a fourth of the data was a lost cause. So I went to my third idea, which here you have the example of the 2 that both look, that looks like a 9, and there are also 2s that look like a 7. My last idea was to create shuffle the numbers so that they aren't from 1 to 9, but kind of using a minimize function, move the labels so that they become more where the linear regression would want it to be. So I created a function that would look at the array and then get the closest one, and then go back to the label it's supposed to be. So I would have my own label array, and it would try to get the closest one and then transform that back into the corresponding number. And then I used this is very messy because this broke down just before I was supposed to present, so I had to kind of just take the data I had successfully gotten last week and just skip the optimization. So I can't really show how the optimization went, but what I did was I split it up into train, test, and validation data, because I used the train to get a baseline, and then I used the validation to optimize the label position using the minimize function. This was, however, a very inefficient method. It took 1.5 hours. I see where the problem was. It copied itself to get this label number, which only when I tried it had a prediction of accuracy of 37%.
Oh, really? I see.
37 and 38.
Do you have the optimizing sequence? What was the optimized sequence of labels? Do you have the optimal reordering? Do you have it?
No, I have the labels that they got. Yes, so the optimized label for 0, optimized in quotation marks, in all honesty, was -3.
Okay.
1 moved up and 2 moved down, probably because it was slightly similar to 0. 3 remained the same, and 4 flew up to 9, and 5 also. There was a tendency to increase the number a lot more than it was a tendency to decrease. The only numbers that decreased was 2, 8, and 0. And the edges went away a lot more than the others, which led to them being very accurate, but everything in the middle got a bit confused. And if we look at the confusion matrix,
wow, so
it is very messy. There are some that clearly improved, or not improved, but had some sort of accuracy. But here in the middle, it got very messy.
But 9 and 4, look at that. Why 9 and 4 flipped? Can you go back to the 9 and 4? Are they very close? Because the 9 is 15, right?
Yes, I do. I cannot tell you why. 9 was the closest one. 4 was the closest one to 9.
But still, there is a big difference there.
But I think it is because the 4s, the ones that were very close to 9, but slightly below half point of 4 and 9 just became 4 because that was the closest one.
Question for you. Question for you. So when you do the minimize, the linear model is fixed, right? So you fix the linear model and you just change the label, or you jointly optimize?
Exactly.
Go ahead.
Exactly. So I fixed the model and just try to optimize the placement of the labels.
So now you know what you should do to get the best result. Right? You should let because the linear model was trained on. No, it's a good. Yeah.
It was an attempt.
I don't need to tell you. Yeah.
No, it was an attempt, and it would have been better if I continuously trained the model. But here we are.
Because as we discussed before, right? So if you have a bad projection, you have a bad projection, right? So if the projection does, if the projection collapses too many things together, then there is nothing. I think this would work if you work it out a little bit more, as the guy said, right? If you had some ridge regression or lasso regression in order to get some coefficients to not explode too much, I think it would work excellently. Yeah.
It would. I still, however, believe it would be worse than was logistic regression and KNN, which we'll come to later. I did consider logistic regression, but since we had a lecture on linear regression, I thought we were locked in on that, so I dropped that quite quickly. Afterwards, we weren't able to do. My group wasn't able to do number 3 because we had one group mate who did it yesterday evening, but was not able to add it to my file. So
no worries, you add it to the final presentation.
Yes. Then I went on and did KNN versus linear regression. I simply trained a normal KNN on the original data set, and I got a precision of 97, which is not that surprising considering this is what KNN is made for. And it's not surprising that it's so much better than linear regression because it's grading it's grading a fish on how quickly it can run up a tree. I continued onto gradient descent. And as you can tell, I did what most other groups did, but I also have a very, very, very low value for my learning for the L, because we would have there was 2 or 3 images that led to a very high prediction. It was in 10 to the power of 7 as a value, which led to an MSE that was very high, so it exploded. And the only way to make it converge was if the I forgot the word for it.
Learning rate. But
the learning rate.
were you batching things, or were you doing one image at a time? How did you do this?
I did all of them at once and to create the beta gradient. Here you can see the dot product. But we would get in not one, but a few outliers that would lead to the MSE being a lot larger. So it would then try to correct it, and then it would overcorrect. And then it will be, the MSE would be very large but negative, and then it would overcorrect again, and it would just explode and never converge. Me and Pierre, a friend of mine who helped me a bit with this process, noticed that it had to do with the data set. When you fetch it from using the way I did with this command, you get a data. It is the same data set, but for some reason we were not able to find out why. It led to these few outliers, which forced us to do very low learning rate. And here you can see the accuracy and the confusion matrix. Accuracy was not better, it was even worse. As you can see, it doesn't look very different than when I trained it just directly. That was all.
Very good, very good.
Any questions?
It would have been nice if that trick worked, but yeah. Elton, ask him some tough questions. Ask him some tough questions.
I don't have any.
Come again?
He said he didn't have any.
You don't have any? Okay, good. Yeah, so for me, I would have just really see the model working. I would have loved to see that the relabeling together with the training of the model, right? Because you can train the model.
Oh wait, actually no, I just looked at the code again. I did train the model again, but I think it just hit. I'll show him quickly. There. Hello. If we look at the function I'm trying to minimize, you see I train it again with the new labels, but I think I would have to use some what's it called.
Okay. Yeah, you have to iterate multiple times, I think.
Yes, I have to iterate
until they converge some.
Yeah, and this was also a very slow process. And then at some point it kind of hit a stop.
Yeah, the thing is that because you use the minimize function. That's because you use the minimize function. But you didn't realize that optimizing the label is also a linear regression problem. That's my point.
Oh, so you're saying I should have linear regressed on the linear? Oh, that's smart.
Yeah,
I didn't even consider that.
Exactly. So the optimizing the label representation is another linear regression, right? Because the matrix then maps the label to the So you do in tandem linear. It's nice. I think it's cute because you take the y, you multiply the y by a matrix, and the y multiplied by the matrix is the optimization of the label. That's what I wanted to see. But
I sadly did not do that. I had not even considered it. I used minimize because
of course, if you don't know, if you just to experiment without thing, but yeah, the tutor solution would have been that one. Yeah.
I will think of that next time, I hope.
No, I hope that you guys realize that the most important thing is always like to be creative in your solutions, right? That's what we try to push, right? It's even if because the students think, oh, when I get my PhD, then it's time to be creative, right? When I know everything, then I can be creative. But the reality is that the earlier you try to be creative, the better it is, because by the time you get to your PhD, your brain is like the one of a horse, just thinks in straight line. Yeah.
I do have a question for future talks.
Go ahead.
So I don't accidentally make the same mistake of putting myself in one thing. Are we allowed to choose what method?
Whatever
or are we
you.
limited?
I mean, you
So
see.
we have a full freedom of method.
So remember that the elevator pitch just give you a small part of the grade, I think. So because your grade comes mostly from your peer review, right? So most of the grade comes from your peer review. So if the peer review find the what you're doing is compelling, it's compelling, right? So my perspective.
So I would have been 100% allowed to use linear logistic regression, for example.
Yeah, I mean, so there is a topic, right? But the point is, So we want you guys to be creative with respect to a certain solution. Now, of course, if you say, "Oh, I just want to solve a different problem," there is nothing to do with your problem, of course. But for example, what you could have taken from the logistic regression are the fact that, for example, again, group one did the closest thing to logistic regression, right? So in that case, they said, let's use multiple labels and then aggregate the labels, and that was the closest thing to linear regression on which they landed, without knowing that they were doing logistic regression, right? So you could have said something like, "Oh, I know that the right thing to do is logistic regression. Logistic regression requires an exponential function. Right now, the topic is linear regression. So let me take a polynomial approximation of the exponential function, and I interpret the coefficients of my polynomial regression as the, you know what I mean? That would have been cool.
Yeah.
That would have been cool. That would have been cool.
So
because
instead
you
of
see
using the optimal, try to make the optimal fit the topic.
Correct. So that it's just, I want to see original ideas, basically. Okay, very good, guys. So let's do a little bit of frontal lecture. Remember that this week there will be no challenge. Elton, do you think that they will benefit? What was the reaction, Julius? Yeah, we said that during midterm week there is no challenge, right? You guys take a break during midterm. So yeah, so remember, so if you want, you can ask Elton to extend the deadline for submitting the challenge for this week to, let's say, next Friday. But I don't think there is much utility, right? You guys have to prepare for the midterm. Anybody wants an extension of the deadline? I don't think it's useful, right?
Do we have to write a report, right? I saw that.
The usual stuff. But you know, of course, the report you write it with ChatGPT, right? It's not that. I mean, it's not that you have to do. It's not that.
Okay.
It's not that you have to sit down 5 hours to it. Okay, good. Then after that, we're gonna have that the groups are formed freely, right? So during midterm week, I will still give a frontal lecture. But if you cannot attend, of course, we just record it and we put it online. So if you don't want to attend, it's fine. And what else? What else? So we'll release a profile for the students, which is the average of the evaluation over the past 3 challenges. So please remember to fill in your form. Elton send the form to everybody. So we're going to have a last form, which is the one for the current challenge, challenge 2. So please try to complete this review quickly, so that we can release the profile of the students. And then yeah, I think this is it for now. Any other question? Any other comments? Tonton? Let me know if you have any other questions. So I know, I'll just tell you now, right? So I know that there are some of you that are looking for summer internship. So I have a couple of positions available. So for the foreigners that are in the class, if you want to do for example, some thesis during the summer here, what we could do is that you could change your status to a thesis student, and you can do your research here. Especially if you have a mandatory thesis, let's say at the end of your bachelor, you could do that. I've done that multiple times for different students. If you go back to Europe and you're looking for a summer internship in Europe, let me know. I'll try to see if I can do something for you. And for the Taiwanese one, right? So there are internships at MediaTek they were trying to set up. So if you're interested, send me your CV. And otherwise, yeah, be mindful that it's very good to do internships. So if you're not applying, you should be applying for internship. Very good. So I'll be as usual a little bit quick in the lecture for today. We're going to do data imputation. And I'll just give you a couple of seconds if you have any question regarding the organization of the rest of the class. Okay. Also, what else? Yeah, I'm gonna be teaching some class on advanced information theory in November and December. So if you're interested, let me know and I'll put you on the Slack channel so you can follow the lectures. What else? Yeah. Always happy to try to help you guys. Okay, very good. So today we just talk about data imputation. It is sort of a lighter topic. It's not very theoretical. So as usual, we just try to have some fun, you know, maybe not some fun, but to say something meaningful and about this. Okay. So dealing with missing data is something that you guys already experienced in the challenge with the asteroids. That was the there was a KNN challenge, right? Because you saw that some of the fields were empty. So some of you threw away the data, some of you filled it in with the mean. So let's see a little bit what is the right policy to use when you're dealing with missing data. Okay, so remember that we had this discussion at the beginning of the course that there is different missing data. The fact that the data is missing could be indicative of some dynamics behind the data itself. So, for example, if there is the data missing in a survey, this could correspond to the fact that people do not want to answer some questions, and they don't want to answer truthfully to some questions. So, for example, if you ask somebody if they cheat, if they ask somebody if they use opioids, even if you are reassured that there is confidentiality in the way you submit a response, or that the data is private, why would you take the risk, right? Why would you admit of some act that is illegal on a survey, right? You would just lie and say no, or you would just not put in the data, and then miss the fact that the data is missing would be indicative of the data itself. But of course, there are some missing data which is completely random, and some other missing data comes from, for example, physical phenomena. So, for example, if there is a speed of something, and this measurement, the measurement of the speed is a certain range. If you go over the range, then the measurement becomes null, and so this could be another way why data is missing. So, what should we do with when we have missing data? You have to first decide if the algorithm that you use can handle missing data. Okay, so for example, if you do a matrix multiplication and the missing data appears as none, then you know that the matrix multiplication is going to fail. But there are some algorithms that actually are able to work with none values. So you have to be able to understand what is the response of your model to the missing data. Okay, so let's go through the Panda. So the Panda function that deals with missing data. So as you can, I'm sure that some of you already saw this. But for example, there is you have a drop NA, right? The function drop NA just simply drop the entries that have an axis equal to 0. You could impute to the mean or to the median, or impute to the most common class. Okay, so let's say that you have a data frame and you have a missing value. What you do is that you fix all the NA value, you fill all the NA value with the mean value of that variable. Okay, so let's say that you have a data set of heights, and some people didn't record their heights, so you have no reason to believe that the people that didn't fill in the height had any reason to hide this data. So you don't want to throw away all the data corresponding to people that miss the height, because it's something that maybe is not so crucial for your downstream task. And so you just impute this value to the mean, right? You say, well, if I cannot guess anything about this specific individual, I will just put it in. Okay? So let's take this simple data set, right? So one simple way to handle missingness on the variable xj is to input the value to 0, to the mean, or to the most variable class. And then what you would do is that you will add a categorical variable, right? This is X1 miss and X2 miss, that keeps track of the fact that the data was imputed. It is very dangerous to augment the data without keeping track of the augmentation, right? So it is always good practice that when you do imputation, you create some binary variable that tell you if the data was imputed or not, because of course you don't want to lose track of this information in case some other use of the data must be made and somebody mistakes your imputed data for correctly recorded data. Okay. Also, you can use this categorical variable in some of your prediction, so you can sort of try to infer something from the type of individuals for which the data was not recorded. As we said, that our concern is also with the fact that maybe there is a group of individuals that miss the data entry for some systematic way, and you want to keep track of this. So let's go back to the example in which you were asking if you were using opioid. It is clear that if you are a person with a safe job and a stable life and you have no criminal records, then for you admitting the use of opioid is not a big deal because it's, let's say, decriminalized. Whether if you are a minority, you are an immigrant, you are in some more fragile social status, then you might want to lie on this aspect. And so you want to be able to do some future inference on the fact that the data was missing, right? So you don't want to miss this. Okay, type of missingness. The source of missing data, of missing values in the data can lead to the major type of missingness. So missly completely random, MCAR, so missly completely random. This is just measurements that are just lost, let's say, for a hard disk failure, in a way which is completely independent from the data itself. Missing and random. The probability that the data is missing depends on the available information on other indicators. For example, consider the example in which there was a speed indicator, and if you go faster than a certain speed and the indicator is missing, then maybe there is some other indicator in the data which is collected, which will be able to predict that the sensor will fail. Okay? Maybe there is an energy sensor, maybe there is some camera sensor, whatever. But this sensor will be able to produce an estimation, which is not completely useless, on whether the data was missing or not. Then there is the missing not at random, which is the probability of missing depends on the information that has not been recorded, and this information also predicts the missing value. As we said, maybe there is a survey, there is a question about opioids, there is a latent variable that determines whether the data will be missed or not. Let's say if you have a criminal record or not, and this information is not recorded. So it's not missing at random, but you cannot infer what was the value. Like you don't have access to the value of the latent variable that was controlling the missingness, and the best thing that you can do is that you can infer the presence of this latent variable. So the best case scenario is the missing completely at random. For example, you do a coin flip to determine whether an entry is removed. This will be, for example, the case of a hard disk failure. You can ignore the effect of this complete randomness, because this randomness can be averaged out in the available data. And you have a lot of options on how to deal with this missingness, but the easiest thing is to impute it, right? So to impute something means to give it some value. And as we said, you can take the mean, you can take the average, and you can take, let's say, some class averages. We're going to discuss them later. So the missing at random, it's still a case that we can handle, otherwise it's more complicated. So let's take another example. So men and women respond to the question, have you ever felt harassed at work at different rates? So, of course, whether you are harassed at work it varies on whether you are a male or a female, right? And some people might not want to answer this question, but the rate at which female versus male will decide not to answer to this question it's an indicator, right? So you can assume that there is a correlation between not answering the question on harassment and being a male or a female. And if the survey records whether the person is a male or a female, then you can infer something about the missing data from the gen. Okay. So what can you do here? Of course, you cannot just drop it, because then you will be dropping a lot of entries and entries that are relevant to you, because of the women that maybe were harassed and decided not to report it. So they prefer to not answer the question rather than to answer no. And if you decide to impute this, then you have to build the proper model for your imputation that exploits the correlation of the data. Okay, so the first thing is to decide how the data correlates to the missing data, how the other feature correlate with the missing data, and then you build a model to impute. So you don't, the imputation becomes a model itself that depends on the available variable. And the missing not a random, that's a worst case scenario. For example, the patient drop out of a study because they experience some side effects of the drugs. If you cheat, you are most likely to not respond when you're asked if you cheat. And you have major effects and major misprediction if you decide not to handle with this missing data. And you can try to sort of mitigate the effects of the missing data by imputing, but the best thing is to create a dedicated variable that tracks the missing data, and it becomes itself a variable in the model. Okay, so you expand your model, you make your model more complicated to account for the possible latent variables that led to a missing data. Okay. So can you actually, by looking at the data, infer what is the type of missingness that that is present? So of course the answer must be no, otherwise we will just tell you that there is a perfect answer to the question of missing data. But in general, you cannot, you can never infer something meaningful regarding the latent variable, right? So some people refer to this as lurking variables, latent variable, remote variable, unseen effects. So there are many names for all the variables that they shape your data collection, and they are correlated with the data collection itself, but you don't have control over, because you are observing the data set out of time, right? You cannot go back and decide to change how the survey was made in the past, right? So we have to live with the fact that we know that there are many factors that are not recorded, that they influence the quality of the data and how much we can learn from the data, but such is life, okay? Okay, now let's discuss a little bit imputation methods. So generally, you have to decide a few things before you move on with imputation. So the first thing is whether the missing values are in the response or in the predictor. So if the missing data is in the response, then you are in trouble, right? So if you have a data set of images and you have a missing label for some of the images, then it's a very complicated thing to go and impute the value of the missing label, right? Because you are really affecting your predictor. If there are some pixels missing in the image because one of the sensors in the camera was broken completely at random, and you just take an average of the PM missing pixel, then that's a much easier imputation to do. Then imputation, it's trickier if you are dealing with categorical variable rather than quantitative variables, right? So if you have quantitative variables, you can always impute to some smooth value, which is, let's say, an average height, an average temperature, or something of the sort. There is an idea of smoothness. There is an idea that even if you introduce some data, the effect of this data will not change the statistic of your collected data, like of your samples. But this is not the same with categorical variables, right? Because if you have to impute, for example, the job of a certain entry, let's say that we go back to the example of the data set of credit cards. You have to decide if somebody is a student or a worker. If you start imputing that all the missing values are students, then this will change the statistics that one observes of the imputed data. It will appear that you have many more students than actually you have. This is simply because you chose one class for imputation and one single strategy for imputation, so it's much trickier to handle. And of course, there is always the question of quantity of missing data, okay? If the missing data is only a small fraction of the overall data set, you can impute with impunity. You can impute with impunity because, of course, this will not have a great effect. But if you have 10, 20% of missing data, then you know that the imputation strategy will really have the potential of affecting your prediction. And so you have to be very mindful of this. And of course, what we always try to do is to have some sort of attempt of imputation. Then we will go back and evaluate the prediction of the model. Then we will change the imputation strategy and see what is the effect on the model. So there is always some sort of evaluation of the effect of imputation on the prediction of the model. This is sort of what you will expect. Okay, so let's see different imputation methods. The one that we already discussed is the simplest one, which is imputation to the mean or to the most common class. So imputation to the mean or to the median will be quantitative, and imputation to the most common class will be for the categorical variable. The discussion is the difference between imputation to the mean and to the median. It's a subtle difference that I'll let you explore on your own. But basically, yeah, their statistical value is different. Okay, their statistical value is different, and let's say they have a different sensitivity to outliers, basically. Then another way that we discuss is to create a specific indicator variable that clearly indicates whether something was imputed or not. We said we do this when we believe that we are in the worst scenarios in which there is some latent variable that controls the missing data, but it's not accessible to us. Then there is the hot deck imputation. So this is the imputation in which for each missing data, you randomly selected and observed data in the dataset. Let's say that you have a missing value in the label X3 and at a certain dataset entry J, then you take all the other dataset entries, you randomly pick one of the label, and then you replace the value in the missing data. Okay. This has a low complexity. This is the complexity of randomly drawing a number in a certain range. Like a better imputation, which has higher complexity, is model imputation. Okay? So you take the feature that you want to impute as a new label. Let's call it y hat, and you take the other observed features, and you build a model that predicts the missing data. Okay? And this is, of course, has a very high complexity because the complexity of predicting the missing data now it's the same. This could be the same complexity of producing the prediction itself. And then there is model imputation with uncertainty. This is when you add some randomness epsilon to your imputed value, and this is because if you use a deterministic prediction, you could run into some additional sensitivity to the imputation method, whether if you add some noise, which is comparable to the noise that you have on the other entries in the feature, maybe you'll be doing less harm because there is not this deterministic relationship between the features and the imputed value that could appear as collinearity, that could appear as low rankness, that could appear as some artifact in the computation of the downstream model. Okay, good. Let's say that let's try to use some model to impute the missing data. So you see here that the dark red is 1 and the bright green is 0.03, but the light green is 10. So how would we go about predicting this this imputed data? So what we could do, let's go back here. So this is the missing data. So what you do is that you divide the model between test and train. And test and train, sorry. So there is X train and Y train, then there is X test and Y predicted, and you build the model to predict all the missing data. So the idea is that, for example, if you want to use K and N, then you will find the neighbors on the X label, and you will produce the missing label as the average of the other two, and we will repeat this operation. If we want to do linear prediction, then we will build another model for doing this imputation. We will use the known label to obtain the coefficients M and B of the linear regression, and you can keep going, right? You can build more and more complicated model, more and more different approaches for creating imputed data. So this is a deterministic imputation, and we're just trying to use the best model to impute the values only on the y-hat. But when we do this, the distribution of the imputed value will be too narrow and not representative of the real data because there is no noise. So you want to add also some uncertainty in the model because the model expects uncertainty, right? The variable as they are collected, they are affected by uncertainty. So as we were saying here, so if you do a deterministic imputation, this will show up as collinearity. So you see here that all the predicted labels, they are collinear, right? They appear as a line. So if you had to look at this data set and you will observe this, let's say, linear behavior in the data, you will be led to believe that in reality, there is a linear interpolation of the data that you could do and you could be successful in doing. But this is because when you did the imputation, you did a deterministic imputation using a linear model, so the linearity of the imputation appears in the feature representation itself. That's why you want to add some noisiness to your imputation so that you don't create this artificial correlation between the data. So what we can do here is that we can add a certain noise, epsilon, which is a Gaussian variable with 0 mean and variance sigma square. And we can manipulate the variance here to introduce noise to the prediction of the imputation method. And we can carefully choose the variance of this object so that you know we limit the negative impact of imputation. So we start by fitting a model that predicts the missing variable using all the other predictors. Then we predict the value of the model. We predict the missing values using this model, and then we just add some noise, and we choose the MSE of the noise as the error that the linear model produces on the available labels. Okay, so this linear model, let's say, will produce an estimate y-hat. So we go and we measure the energy of the estimate y-hat on the data which is present in the data set. Then we match the power of this error to a Gaussian random variable with the variance equal to the MSE, so that we know that the correct noise to be added to the label is a Gaussian noise of value sigma square. As always, we like Gaussian models because they are simple to deal with. Gaussian random variable, they're also simple to generate. And the other aspect is that if we believe that there are many independent factors that contribute to the error in the recording of the label, then the Gaussian distribution will arise from the law of large number, right? So if many independent effects they sum together, then the effect of the sum will be a Gaussian random variable. So we have the law of large number to reassure us that the assumption of the Gaussian noise is a meaningful assumption. Okay, very good. So we can do KNN regression. So we can use KNN to impute the value that mimic the error in the observation. So how do we add noise to a KNN imputation? So we can use k equal to 1. That's not very interesting because if we do k equal to 1, then we have the same noise on the label with the closest one. We can usually use any other value of k, but we randomly select a subset of the neighbors. And this can be done with some equal probability or with some weight, right? So we can figure out a KNN model that is affected by some random effect, some random choice, which reproduce the effect of the error. Notice that we have to do this because if we had to obtain a measure of the noise on the KNN regression, that will be very heavy, right? So we will have to do basically a leave one out type of correlation, right? So we will have to do cross validation. We will have to do a lot of work to obtain a measure of the reliability of the KNN estimator over all the data in such a way that we can recover a measure of the MSE error that is affected by the model, right? Okay, and then does not lend itself to an estimation of the prediction error, which is as easy as in the linear regression case. Okay, so if only one variable is missing in one entry, then life is easy. But what if the prediction variable as a little bit of missingness, right? It's meaning that you have multiple observations that are missing. So then we have to use an iterative process where we start to impute x1 based from x2 and xp. Then we impute x2 based on x1, x3, and xp, and you continue down the line until you have all the, let's say you have all the models that are able to fill in the missing data in your data set. Then what is the issue with this approach? Of course, not all data will be imputed in one pass, right? So first you will go through the missing data and impute x1, then you will go through all the missing data and impute x2, and so you have to repeat this imputation procedure until you fill in all the data. And of course, this repetition has the possibility of cascading down the effect of your imputation on the model, right? So the models have to be built according to the available variables. If the available variables have been previously imputed, then it's possible that you stray away from the true label simply because you use imputed data to produce other imputed data. But of course, you cannot have, it will be too expensive to have all possible models that impute from all possible missing data from all known data, right? Because then here you will have a combination of, let's say, p possibly imputed data, and 2 to the p, you need 2 to the p model to consider whether in this imputation you can, if all the data that you use for imputation have been themselves missing data. So it's very, very tricky things to do. And let's discuss what is the issue with treating your now complete data set as a mixture of observations that have actually been previously imputed as simply all observed value. Any inference or prediction carried out will be tuned and potentially overfit on random entries imputed from missing entries. And how can you prevent this? Okay, so the idea is always to do multiple imputations. So you run your inference algorithm on some imputed data. You return to your imputation method. You change your imputation strategy. You maybe average over different noise realization of your imputed model. Repeat the fitting. Do some cross-validation. Of course, we have seen this trick before when we were talking about cross-validation. If you're doing some operation and you want to know what is the effect of a specific imputation strategy, what you have to do is to go around, change your randomness, change the random selection that you have, and try to reproduce the same calculation to see what is the distribution of your model. And based on the distribution of the parameters of your model, you can infer something on the effect of imputation on the prediction. Okay, very good. Any question on this? Let me ask. Any question on this? Any question on this? As I said, pretty easy class. I think we stop for now. If there are no questions, we stop a little bit early because we already. Yeah, I think most of you guys are already being booked after 2 hours and a half of this. So next week we'll continue with the frontal class. Please remember to fill in the form. If you want to start forming your group now, go ahead. If you are a leader and you want to form your group, remember to keep the name of your team so that we, instead of calling group 1, 2, 3, 4, 5, A, B, C, D, we call you by your group name, which I think it's more human and humanizes the students. Otherwise, as always, I'm going to be here in chat if you have any questions. Remember, if you have any idea for internship or interest in internship, let me know. I'll try to do what I can for you guys. And otherwise, good luck in your midterm exam. I hope that you guys don't have 15 midterms in 1 week, but such is life as a student in Taiwan. And yeah, I'll see you next week if there is no other question. Ciao, guys.
Okay, bye bye.
再见，再见。Elton, how is the lab today? Are you in the lab?
No. So I think I'll send a Google form for them to fill out the group.
Yeah. Yeah, because after that we should have. You saw what we did last year, right? So we take the grades for each of the possible roles, so that we give like a profile that says, "Oh, this guy is a very good thinker," right? So that then people, if they haven't been with a certain person before, they can see what is the profile of the person that they want to put in the group. Yeah.
So
And
so
also,
you mean in the cross-team evaluation you should
the intra-team evaluation. Yeah, in the intra-team evaluation, you can take the average of the score that they got as a certain role, right? Because they choose the role and then they get a score for the role, right? So you can just put the number.
So in the intra team, you should have a thinker and then
Correct.
And then yeah, but I didn't see the.
So it was not in the form.
Yeah, it was not in the form. So I just.
Because it should have been in the form, but it was not there. We fix it next year. So in the intra-team evaluation, they just evaluate the students and that's it. Between 1 and 10.
Yeah, 1 to 10.
No problem. Next year, then we have to add that part. Gosh, I forgot. Very good, very good. And then, so what you do is that you release only the average, so that the students do not see which grade they got, because since it's only 3 grades, and they think that somebody gave them a very bad grade because they are, some personal reasons, and they are not aware of it. Right? So that's also something to keep in mind. And then, yeah, that's it. I think that's it. So, but I think that so we have 3 challenges with 5 people each. Hopefully, already everybody knows everybody else, right? That's it. There should be not too much issue in the students choosing their own team members. Yeah, I'm interested to see the dynamics, right? I wonder, because the dynamic that I expect, Elton, is that the girls will form a group with other girls. That's my expectation. That's my experience in the past. So that's why usually we try to choose leaders as the females, so that then they cannot form a group altogether. That was my experience in the past. Okay, very good, Elton. Thank you for the help. Yeah, so Francisco, in general, we go through the evaluation, and unless a leader receives a very poor evaluation in the inter-team evaluation, we will keep the leader. If you want to be a leader and you're not a leader, then you let us know. We look at your performance and we just decide. Because we would like to have 4 leaders, and so we already have 4 leaders. I think one of the leaders didn't receive very good evaluation, so we are thinking about changing the one leader, right, Elton? That's the only thing. That's all. Okay, I'll mute myself. If you have any questions, let me know. Hi, Francisco. Hi, Francesco. Aaron Echaure. We see you soon.
Hi, I have a quick question.
Go ahead.
Of course, but I have a friend, she's doing data science.
Okay.
And you mentioned that you have internships. And I'm wondering if I can that you might be able to do some have context for internships.
But so this person is Taiwanese. Where is this person from?
She is from she's in Europe, based in Europe.
Which country?
She is originally from Croatia, but is currently in Netherlands, in the same university as me. And I was wondering if I could.
Tell her to send me her CV and I'll see. So because
Yes.
I'll just have to talk to her, because if you are abroad, you actually get paid to come to Taiwan to do research. So that's very interesting for you guys. That's why if you want to stay for the summer, it's very nice for you guys. And a lot of universities from the Netherlands. It's called NYCU, OIA, internship. Let me check. Internship opportunity. Let me see if I can find it. Just a second. Enterprise internship. What is this? Elite internship. NYCU. Check NYCU elite internship. Within us at March 28. Let me see. You have to look at the. You have to look at the internship. No. Let me check. Okay. OIA. God damn it. Then we go to the short-term students, international students. This one here, inbound exchange program, should be this one here. This one here. So also for you, if you want to stay during the summer, you can.
Thank you very much.
Should be this one here. No, this is for the courses. Which one is it? Gosh, this website, too many things. Short-term, and I see your scholarship. A Taiwan Europe Connectivity Scholarship. Is this one here? Timeline, motivation letter, admission, but they give you money, right? Scholarship amount, 4 months, 16,000. This is it. Yeah. But this is only for Europe, yeah?
Yeah. This is, I'm guessing this second link is for people who are studying here for a semester or something.
This is for, wait a second. Short-term research, yeah. This is. Yes, and notice that they ask you to teach at a local junior high school for 2 or 3 sessions. Gosh.
That would be interesting.
That would be very interesting. So let me give it a chance for all the EU students that want to do a summer internship here. Look at this. Which university you are from the Netherlands? Remind me again.
University of Twente.
Twente, yeah.
So I am allowed to give her your contact information.
Yeah, of course.
I just wanted to double check since she's
not many people talk to me. Trust me. Even my wife is not very motivated to talk. No, I'm joking. Okay, good. But yeah. So do you have do you have a thesis requirement, for example, for your course of study?
Yeah, it has to be associated with electrical engineering, which this isn't really. But I do have already have some people I'm talking to about thesis.
No, yeah, because that's another option, is that you can ask them if you can do an academic internship instead of industry internship. So, for example, if you are motivated to do a PhD, right, you would much rather do a research internship than a company internship. But I know, I'm sure that you know already. And so if you want to stay for some research, if you ask for a research internship, usually they let you do that. Anyway, it's up to you. Yeah, just letting you know.
Thank you very much. And
Yeah,
thank you for today's lecture.
because I think the NXP has something here. But the point is that the NXP, because NXP is very Dutch. So I think that the office here, they just do support and sales. They don't do research. But you could try to talk to them here to see if they have some engineers that are developing some stuff here. Of course, there is also ASML. You could try to talk to them, and because they have some people here, but again, I think they only do support. But maybe there is some data collection that they want to do locally that would be interesting. I mean, my suggestion is that if you like, because I assume that you like it here, right? Because it's a very, very safe assumption. You try to find, because there are many Dutch companies that they work in Taiwan because of the cheap manufacturing industry. And you will ask if there is some office that is doing some data collection, some development that you can talk to.
Yeah. Thank you very much.
Okay, talk to you soon. Ciao, Elton. Let me stop the call. Let me stop the recording. Ciao, 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 guys.
Ciao.
Ciao, 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 ciao.